Welcome to this video on Zero Knowledge Proof. My name is Karthik, and in this video we will explore what Zero Knowledge Proof is, how it works, and some of its applications in various fields of computer sciences. So, what is a Zero Knowledge Proof? A Zero Knowledge Proof is a cryptographic technique that allows one party to prove to another party that they possess certain information without revealing the information itself. This may sound like a paradox, but it is possible through the use of clever mathematical techniques, tricks, and protocols. The idea behind Zero Knowledge Proof is to provide a way for parties to verify information without compromising privacy or security. Zero Knowledge Proofs were first devised by MIT researchers Shafi Goldwasser, Silvio Michael, and Charles Rakoff in the year 1985 in their paper The Knowledge Complexity of Interactive Proof Systems. The paper introduced key concepts including an interactive proof (IP) hierarchy and conceived the concept of knowledge complexity, a measure to see how much proof is transferred from the prover to the verifier. Perhaps the most importantly, they gave the first zero-knowledge proof for a concrete problem when they demonstrated how to construct zero-knowledge proofs for any NP set with any commitment scheme. Two other researchers at the University of Chicago and at Ronad University in Budapest, Laszlo Babi and Shlomo Moran, also published a paper on the topic Arthur Merlin Games, a randomized proof system and a hierarchy of complexity classes in 1993. These two papers earned all five researchers the 1993 Gödel Prize, an annual award for outstanding papers in the era of theoretical computer sciences. Fish, Lapidot, and Shamir introduced the factor of witness indistinguishability in 1999, which added an important design technique for zero-knowledge proofs. Oded Goldreich has contributed knowledge and foundations to the study of sequential, parallel, and concurrent composition of zero-knowledge proofs at the Weizmann Institute of Science. Russell Impalzigo and Monty Young provide proof that, assuming unbreakable encryption, that anything can be proved by an interactive proof system can be proved with zero knowledge. So how do we implement zero knowledge proof? There are many different ways to implement zero knowledge proof, but most methods involve a series of interactions between the prover and the verifier. The prover wants to convince the verifier that they possess certain information without revealing the information itself. To do this, the prover and the verifier engage in a protocol that involves the exchange of messages and mathematical challenges. Through this protocol, the verifier can be convinced that the prover possesses the information without actually seeing the information itself. Zero-knowledge proofs are proofs that are both convincing but do not yield anything beyond the validity of the assertion being proven. Zero-knowledge proofs or protocols are important because they do not require the party to reveal extra key information or any other information in order to prove that they know a specific value. This security has made zero-knowledge proofs important in cryptography, private information security, and financial transactions and blockchain applications. Zero-knowledge proof protocols originally require interactive input from the verifier and prover, whether that be a people or computers. These inputs are challenges to the verifier to prove they do in fact know the claimed knowledge without actually revealing it. Zero-knowledge protocols are probabilistic assessments, meaning they don't have to prove with complete certainty. While zero-knowledge proofs can enable almost complete assuredness, the prover knows the value. It is not a mathematical proof because of the small probability, the soundness error, that the cheating prover is able to convince the verifier of a false statement. An example of this soundness error would be if the prover was somehow able to guess the correct answer 1000 times in a row. A zero-knowledge protocol must satisfy the following criteria. Completeness. If the input is valid, the zero-knowledge protocol always returns true. Hence, if the underlying statement is true, the prover and the verifier act honestly, the proof can be accepted. Soundness. If the input is invalid, it is theoretically impossible to force the zero-knowledge protocol to return true. Hence, a lying prover cannot trick an honest verifier into believing any invalid statement is valid, except the tiny margin of probability. Zero knowledge. The verifier learns nothing about a statement beyond its validity or falsity. They have zero knowledge of the statement. This requirement also prevents the verifier from deriving the original input, which is the statement's contents, from the proof. There are two types of zero-knowledge proofs. Interactive zero-knowledge proofs. In this type of zero-knowledge proofs, the prover and the verifier interact several times. The verifier challenges the prover, who provides the replies to these challenges until the verifier is convinced. Non-interactive zero-knowledge proofs. In this type of zero-knowledge proofs, the proof delivered by the prover can be verified by the verifier only once at a time. This type of zero-knowledge proofs require more computational power than the interactive zero-knowledge proofs. Let's dig deep into these two types. What is a non-interactive zero-knowledge proof? Traditionally, many zero-knowledge protocols can be made non-interactive, aka non-interactive zero-knowledge (NIZK) proofs. This means that the prover only needs to run a program talking fxy as input and outputs the proof pi. Any verifier with fy pi can verify it and be convinced that the prover indeed knows x without seeing it. The workflow of an NIZK proof resembles a digital signature. The signer signs a public document using its private signing key and generates a signature. Any verifier with the document, signature and verification key can check the validity of the signature. Non-interactive zero-knowledge proofs have found many applications in the blockchain domain due to their attractive feature of transferability. The prover, without knowing the identity of the verifier, can generate one proof that can be used to convince anyone who receives it. NIZKs with very small proofs are generally categorized as ZK snarks. They are particularly suitable for open systems where there can be many verifiers interested in checking the proof. In this case, the proof only needs to be computed once and verified by many verifiers cheaply. However, these advantages of second zero knowledge come with some downsides. Second zero knowledge proofs often have a high overhead on the prover side in computation and memory. The resource needed to prove a function is orders of magnitude higher than what is needed to evaluate the function in the clear. Many non-interactive zero knowledge proofs have a consistent sized proof, while others have a polyalgorithmic proof size. We treat them all as ZK snarks. Now let's talk about interactive zero-knowledge proof. Another type of zero-knowledge proof protocol is interactive zero-knowledge proofs. The Coke or Pepsi example is an interactive zero-knowledge proof between the prover and the verifier. The two parties need to communicate in rounds with information flowing in both directions throughout the protocol. Outside the zero-knowledge domain, interactive protocols are commonly used in practice. For example, for a user to authenticate via password, they can run an interactive protocol as follows. The server spends nonce y to the client. The client replies to the server with an h variable, which is called a hash function. It would be a cryptographic hash function, which contains the username, password, and the nonce. The server checks if the value is valid by recomputing the same value locally. An interactive protocol allows the server-generated nonce and thus prevents replay attacks, where an attacker captures the message and resends it at a later time to the server for authentication. Allowing a round of interaction is crucial because preventing replay attacks would be much more difficult if the password authentication only consists of one message from the client to the server. Privacy has always been viewed as a valuable feature within the cryptocurrency community. It is the precursor to fungibility, which is necessary for a widely used form of money. Similarly, most crypto asset holders don't want their holdings and transaction history to be completely public. Among the various cryptographic techniques aiming to provide privacy to blockchains, the ZK snark and ZK stark proofs are two noteworthy examples. ZK snark stands for Zero Knowledge Second Non-Interactive Argument of Knowledge, and ZK stark represents Zero Knowledge Second Transparent Argument of Knowledge. ZK snark proofs are already being used on Zcash on JP Morgan Chase's blockchain-based payment system and as a way to securely authenticate clients to servers. But while ZK snarks have made significant headway to being well established and adopted, ZK stock proofs are now being touted as the new and improved version of the protocol, addressing many of the previous drawbacks of ZK snarks. Stocks can offer enhanced security through the non-requirement of a trusted setup, but it can take longer to verify and can therefore be considered less efficient as a result. They also have larger proof sizes than snarks, which means that verifying stocks may take more time and may be more gas intensive than snarks. On the other hand, as the proof for stocks can be verified without relying on any external parameters, stocks can be easier to audit than snarks, though this may depend on the individual implementation. Unlike most snarks, stocks rely on hash functions which are considered to be quantum resistant. Let's take a look at how zero-knowledge proofs are used. Let's take the case of the Alibaba cave. Let's say we have a cave with a gate that has a secret code, and only Alice knows the code. She has to prove to Bob that she is the only one who knows the code without actually telling him the code. So Alice either takes the two options A or B and stands over there, while Bob does not know which route she has taken and he stands at the entry. Bob then tells Alice to either come out of A or B, and he tries this multiple times. If Alice comes out at the same place where he calls out, this would mean that she knows the code to the gate, because if Alice takes A route and he tells her to come out of B, that means that she knows the code, but Bob does not know what the code is. Hence, without zero knowledge, Alice proved Bob that Alice knows the code. Let's take another example. Imagine you have a friend who is colorblind and can't see the difference between a green ball and a red ball. To him, the balls have the same color and you want to prove to him that they are in fact different. He doesn't need to know which is red and which is green, just whether or not they are different. So if you give the balls to your friend and take note which ball is in which hand, then your friend puts the balls behind his back, chooses to either switch them around or not. After that, he shows them again to you, and now you have to tell him whether or not the balls have been switched from their hands. If you are not colorblind, then this is very easy to do because you can see the difference in color. You can clearly tell when the red ball was moved from his left to the right hand, for instance. In fact, we can determine that with an accuracy of 100% because again, we see difference in colors. But wait, your friend is suspicious, the balls look the same to him and he thinks that you are trying to fool him. After all, you have a 1 in 2 chance of correctly guessing whether he switched the balls. Those are pretty good odds, so you decide to run the experiment again. Your friend hides the ball behind his back again and then randomly chooses to switch them or not, and then presents them to you again. Again, you can see this straight away that if he has switched them or not. But if the balls would be of the same color, you would have to guess again. And now your chances of guessing correctly have been halved, and now it's just 1 in 4 or 25%. Repeat this process 10 times and the chance of you guessing correctly drops to just 0.09%. This is probably so small enough to convince your friend that the balls are indeed a different color, because you just can't be that lucky. But of course, you could keep on going. Each time you repeat the process, your probability that you're cheating decreases further. So that's it. We have proven to our friend that the balls have a different color. But this proof does not convey the actual color of the ball to our friend. Hence, we have the name zero knowledge. Let's move on to the applications part. Zero knowledge proof has many potential applications in areas such as online security, privacy, and cryptography. For example, zero knowledge proof can be used to authenticate users without requiring them to reveal their passwords to other sensitive information. It can also be used to protect privacy in online transactions by allowing parties to verify information without revealing sensitive details. In addition, zero knowledge proof can be used in blockchain technology to enhance security and privacy. So let's consider Bitcoin. So all the transactions of Bitcoin and its information is public. So if you buy or send Bitcoin from one account to the other, you can see exactly who sent that transaction. You can see the amount of it and when it was sent. So you can go to any Bitcoin Explorer and check out the information. But there's a big benefit to Bitcoin, which is decentralized currency. So there's no central intermediary controlling the data, and it's on blockchain, but it's still public. You can still see all the information about it. So that's a problem, which is the data is available to everyone freely, right? So let's look at an alternative. So you could use a bank, right? And you can use the bank to keep all your data private. And if I want to send money to somebody with a bank transfer, write a check or use a debit card or anything like that, that all collects transaction histories, and it's private but not public, but it's still something that's stored in somewhere. The data is centralized, but it's still kept in the bank, and that's another problem. So what we need is a best of both worlds. So what we can use is something like cryptocurrency called Zcash. So Zcash gives you private transactions where you can send cryptocurrency without you knowing, without anyone else knowing who sent it or the amount of it that was sent it. None of the information is public, and you don't need to store it on an entity, and you can still leverage blockchain technology. So you're not giving all the data away. So it's a really good middle line. Blockchain. The transparency of blockchains such as Bitcoin and Ethereum enable public verification of transactions. However, it also implies little privacy and can lead to de-anonymization of users. Zero-knowledge proofs can introduce more privacy to public blockchains. For instance, the cryptocurrency Zcash is based on zero-knowledge second non-interactive argument of knowledge, also called as zk-SNARK, a type of zero-knowledge cryptographic method. Another example is also zero-knowledge scalable transparent argument of knowledge, zk-STARK, which is used in the Ethereum blockchain and provides privacy and scalability. Finance. ING uses zero-knowledge proofs that allow customers to prove that their secret number lies in an unknown range. For example, a mortgage applicant can prove that their income is in the admissible range without revealing their exact salary. Online voting. Zero-knowledge proofs can allow voters to vote anonymously and to verify that their vote was included in the final tally. Machine learning. Zero-knowledge proofs can allow the owner of a machine learning algorithm to convince others about the results of the model without revealing any information about the ML model itself. Ethical behavior. One of the uses of zero-knowledge proofs with cryptographic protocols is to enforce honest behavior while maintaining privacy. Roughly, the idea is to enforce a user to prove, using a zero-knowledge proof, that its behavior is correct according to the protocol. Because of soundness, we know that the user must really act honest in order to prove to be able to be a valid proof. Because of zero-knowledge proof, we know that the user does not compromise the privacy of its secrets in the process of providing the proof. Zero-knowledge proofs come with their own set of challenges. No 100% guarantee. Even if the probability of verification by the verifier while the prover is lying can be significantly low, zero-knowledge proofs don't guarantee that the claim is valid 100% of the time. As demonstrated above, probability of a prover lying decreases in each iteration of the ball picking process, but can never match zero. Thus, zero-knowledge proofs aren't actually proofs in mathematical sense. Computation intensity. Algorithms used are computationally intense as they require many interactions between the verifier and the prover in interactive zero-knowledge proofs, or require a lot of compilation capabilities in non-interactive zero-knowledge proofs. This makes zero-knowledge proofs unsuitable for slow or mobile devices. So, in conclusion, zero-knowledge proof is a powerful cryptographic technique that allows parties to verify information without compromising privacy or security. Though the use of clever mathematical tricks and protocols, zero-knowledge proof provides a way for parties to authenticate and verify information without revealing sensitive details. This has many potential applications in areas such as online security, privacy, and cryptography. Imagine if we could just write in our passwords, but not actually send the password data from the user to the server, but then the server authenticates you as a user. There is no data transfer of password, so there's no possible way anyone can breach your data. Zero-knowledge proofs are rapidly gaining attention because of their unique properties of privacy preservation and scaling potential. The increasing application of this technology in blockchain, cryptocurrency, and DeFi will likely bring more innovative services that greatly benefit users. The zero knowledge proof are expected to play a crucial role in creating DApp ecosystems that are more secure, private, and efficient. I hope you enjoyed this video on zero knowledge proof. Thank you for watching.